We're going to talk about Newton's second law now as applied to the NTB coordinate system. And we recall from earlier work that if a particle is traveling along a path, a curved path, that it's always going to be tangent to the path. The actual velocity is going to be tangent to the path, and so we define the tangential direction as positive in the direction of motion, and the normal direction is positive, pointing in toward the center of the circle or the radius. As the path changes radius over here, we again see the velocity is still always tangent, and the normal direction now points in. The coordinate axis travels along with the particle. And if we have a particle sliding down a slide this way, again, we will have velocity tangent to the path, the tangent direction of the coordinate axis points in the direction of motion, normal always points in. And recall that our equations are the velocity in the tangential direction is ds dt, which is s dot, never a normal component of velocity, meaning perpendicular component of velocity. The acceleration in the tangential direction is dv dt, and which is v dot. Then the normal component of acceleration is v squared over rho. Recall also that the equation for rho is there. And also some things we did before is that if the path happens to be a circular path, then the distance it travels is rho theta, where theta is in radians. If it's a circular path, then of course r is a constant. And now, the equations of motion for the NTB coordinate system are that some of the forces in the tangential is mass times acceleration in the tangential, which is mv dot. Some of the forces in the normal direction is mass times acceleration in the normal direction, which is mv squared over rho. Now, some of the forces in the b direction. The b direction is perpendicular to the paper, so it's coming out of the page. And what we want to suggest is that, again, the path defines the direction, and so the tangential direction is always going to be essentially a two-dimensional. The normal and the tangential direction are essentially a two-dimensional kind of look, suggesting that if it leaves the path going up in this direction, then it's leaving the path. So we can say that there is no acceleration in the b direction, in the perpendicular direction. Therefore, the sum of the forces in that direction have to be equal to 0. All right, so we're going to start with a couple of easy problems here. Here's a young man who's on this little swing set, and we want to find a couple of things. So at the instant theta equals 60 degrees, he's right here. He's got a center of mass here, and he's got a downward speed of 15. And we want to find the rate of increase of his speed and the tension in each of the two ropes that are holding the boy. He weighs 60 pounds. Now, first thing we do in NTB problems is we draw a free body diagram. So let's just do that. Let me draw it right over here. So I'm going to say that the boy looks like this. Actually, let's make it a little steeper angle. We're going to say that it looks like this, the boy. And here is his ropes holding up, and there's a tension in those ropes. All right, so we'll just draw the tension this way. We've defined angle theta here. We've got an mg coming down here. All right. Okay, and we can suggest that this is going to be because the velocity is going in this direction, we'll call this the tangential direction, and this going back in here the positive normal direction. So that's the n-axis and the t-axis going like that. Okay, if that is angle theta, with the angle with the horizontal, then we have this kind of a component and this kind of a component, and we're going to say that this here is angle theta as well. And you can see that as theta gets larger, then theta is going to get larger at the bottom. So we can convince ourselves then that this is mg cosine theta, and this is mg sine theta. Remember again, mg is always the hypotenuse of the right triangle, which shows that. All right, so to solve our problems here, we need to find the rate of increase of the speed. So we're really looking for the tangential acceleration. That's what the rate of increase of the speed is. All right, so let's sum the forces in the tangential direction and say that that's equal mass times acceleration in the tangential direction. Forces in the tangential direction, well, I've got that mg cosine theta. If I look at everything else, there are no other forces, and that's going in a positive direction, so mg cosine of theta is the only force I have in the tangential direction. So that's equal to our mass times acceleration in the tangential direction. So again, this is very simple. Acceleration in the tangential, AT is equal to, those masses cancel, it's going to be equal to G cosine of theta, which is equal to, in this case, we're in the English system, that would be 32.2 feet per second squared. That's my G, and cosine of 60. And so I can say AT is equal to 16.1 feet per second squared. All right. So that is the rate of increase of the speed. All right, how about the tension in those chords? That would be solved by some of the forces in the normal direction. So again, that's positive going up, negative going this way. So some of the forces in the normal direction equals mass times acceleration in the normal direction. On the positive, I've got plus. And I'm going to say that this is 2t because it says that there are two chords holding, on the swing. So I'll say 2t is going up in that direction minus mg sine theta. That's coming down this way is equal to mv squared over rho. All right, so I can set that equal to 2t, and that's equal to mv squared. In this case, it is a constant rho and plus mg sine of theta, and we can fill in the gaps here. This is equal to, I can factor out my m, so I'm going to say that that is equal to, well actually, let's keep the m in there, and we can do a little exercise here. Since this is in the English system, we'll say that the mass is going to be equal to the weight divided by gravity. So I'm going to say that his mass is equal to 60 pounds over 32.2. His velocity is, it's given in the problem as 15 feet per second squared. So that's 15 squared, and divide that by rho, which is 10 feet. Plus mg in the English system is his weight. So his weight is 60 pounds. That's mg, and then sine of, again, 60 degrees. And I solved that for tension, and T is equal to 46.9 pounds. That would be the tension in each chord as we go forward through that. All right, that's how we solve the simpler ones. I think right now let's do a free body diagram exercise. This is a real important skill in doing NTB problems and in all of these F equals MA problems. But let's say that we got our roller coaster rolling down the hill, sliding down the hill. To draw a free body diagram of this to properly analyze this thing, so let's just draw it over here, and I'll draw like this. We know our velocity is going down the hill, and so I can say that the tangential direction goes that way and the n direction goes that way. So I'm going to say this is the n axis and this is the t axis, the positive t axis. We're going to have an mg coming down this way. All right, it's always necessary in these problems to find an angle, or the angle theta, that these objects make with either the horizontal or the vertical. So I'm going to call this the angle theta, and which means that I draw a cosine component. That means that's the angle theta. It's nice to define the angle theta relative to the horizontal, because that way we draw two vertical lines and we cut it with that straight line there, and we can see that that's angle theta and that's angle theta. It's really simple to do that. That would make this the mg cosine, and then we know that the sine component then goes down the hill this way. That's mg sine. Now we also have a normal force, something keeping the roller coaster from just going straight down. So the normal force comes up like that. All right, so I think that pretty much completes our free body diagram of that. How about this on the circular path? Same kind of thing. I'm going to draw my little path like this with a guy like this. In this case, the angle theta is defined with the horizontal instead of the vertical, so it's not much different. You just draw the same mg coming down. You have to draw a component in this direction, a component in this direction, and a normal force. And So in this case, because the angle here is that, I'm just going to, just for reference for your, because it makes it easier, I believe, to draw it with the horizontal or with the vertical. So I'm going to call that alpha, which means that that is alpha, which means that that is theta. And again, if the problem expects that you define it in terms of theta, then this is going to be mg cosine theta, and this would be mg sine theta here. Right? The side adjacent would be the cosine. All right, and then when you have a problem that looks like this, there's a whole bunch of different kinds of questions that could be asked with a picture like this. I mean, if this box has got a horizontal speed here, you might find out how far it goes up the hill before it comes back down. You might find out where on the arc that it actually becomes a projectile and does this. You may need to find out the speed that it takes to get it up here without it falling without it becoming a projectile, or maybe the speed that it takes to get it all the way around. All right, so there's a bunch of questions that could be asked. The important thing is to draw a proper free body diagram, and the best way to do this is to draw it at the down in here in the less than 90 degree stage and call it a generic free body diagram, and then you can evaluate it at various angles of theta. Again, theta is the angle that it makes with the vertical, so if you need to do something up here at this angle, then theta is more than 90 degrees, but that's okay. If you draw the free body diagram down here in the down in this part, you generally don't go wrong. So I'm going to call this theta, I'm going to call this mg, I'm going to call this theta, this mg cosine theta. I'm going to call this mg sine theta. Always going downhill, and then the normal force that looks like that. Obviously we have our tangential direction and our normal direction. Because I didn't actually put that on here, which I should have. This was the tangential direction and the normal direction for the skateboarder.